Let's take a look at liveness analysis for our next lesson. We have figured out the flow of program. Now we have to keep track of the variables used in each block. When do they get defined? When do they get used? This brings us to a very important aspect of compilers called live variable analysis, which is the topic of this lesson. This analysis tells us about the ranges during which given value is active and which value needs the register during which interval. So to review, here is the structure of the compiler that we have been looking at. We looked at the parser, the scanner, the semantic analysis, and then all those working together either produce semantics errors or the syntactic error or the lexical errors. And of course, if the program is error free, then they work together and converted it into the intermediate representation. And from that intermediate representation, we are going to do certain analysis, put that in terms of a control flow graph, and then do the code generation out of that. So collectively, all these phases which work together, which are shown by this big black box here, are called as the backend. The other phases that are shown over here before the intermediate representation are called as the front end. So the compiler is separated into front end and back end. It gives us an ability to work with multiple languages, convert them into the same representation, and then leverage the backends which are designed for different target processors on them. That way we can target, for example, C, C++, Java, and many other languages into the same representation, and then we can use a common backend which is for, let's say, something like x86 on them. And so we don't have to write 3 different compilers, but we write 3 different front ends and leverage the same backend. So that's the idea behind intermediate representation, and also the backend which is specific for a given processor. So let's take a look at what exactly that black box backend really means and what are the essential tasks which are supposed to be there in that backend. The first one is instruction selection. The second one is optimization and register allocation. That is a very important task for bringing values from memory, keeping them in registers as much as we can, and then operating out of registers on those values, and then storing the results back into the memory. For RISC architecture, this phase is really critical. Let's take some deep dive in terms of what these phases really mean. So instruction selection is a phase which maps the lower level IR into the actual machine instructions by selecting the instructions for implementing each of the IR operations. This is not necessarily a one-to-one mapping. We have differences here in the architecture, such as CISC architecture, and which could have a lot of addressing modes. So multiple IR operations could be represented by a single instruction. On the other hand, in RISC, we could have each of the IR operations being implemented by multiple simple instructions. Now, the second phase of this, which is really critical for performance, is to be able to operate the values out of registers, and these are called as register allocation phases. And so the goal here is the lower level IR assumes unlimited registers, unlimited amount of memory to store these values. And the goal of this phase is to map these values to a finite number of registers. As you know, typically we have about 32 floating point registers and 32 fixed point registers or integer registers. And we have lots and lots of values in the program in the IR. And therefore, our goal is to keep the best values which have the best benefit in these registers. And so that is the goal of register allocation phase. And the goal here is to maximize the use of registers and reduce going to memory frequently. So again, going back to these 2 different parts of the backend, instruction selection is mostly a local property. We look at each of the IR instructions and we can generate certain code out of them. In some cases, we may have to build a DAG or a tree out of IR operations and then pick CISC instructions which can cover multiple IR operations using pattern matching. Register allocation can also be formulated as a local problem in terms of keeping the values for short durations in registers, but it is much more effective as a global problem for keeping the values maybe throughout the duration of a function call or large parts of the function call, etc. And that's why this problem is formulated in a different way and is solved in a more global sense. Local means local to basic blocks and small sequence of statements. Globals typically means to the entire procedure, covering the entire procedure. And the second approach is what is typically taken. We want to work on the control flow graph, and using control flow graph, we want to determine these values which should be kept into registers through large durations of the function or the procedure calls. And one of the key things that happens is this is not really confined to a given basic block. This is confined to a whole function or a procedure, and it must take into account the control flow graph that we introduced in the last lecture. So therefore, first let's review the control flow graph concept that we had introduced and looked at in the last lesson, reinforce our concept, and then from there take a look at the problem that we are going to solve for register allocation in this lesson. The control flow graph, as you know, is directed graph representation of the program, and each node and edges represent the flow of control, and we can determine some control flow properties here and therefore use this particular abstraction for doing some analysis in terms of different possible orderings on execution of the program and trying to do certain optimizations such as register allocation on it. To recap, what is the CFG? The nodes are basic blocks, which are consecutive statements of non-branching parts of IR, and the edges represent flow of control, and we can jump from one block to another. Each block may have multiple incoming or outgoing edges. And so having understood the CFGs, now let's delve a little bit deeper inside the basic blocks and see what is going on, and that is what we are going to use in this lesson to determine the deeper properties of uses of values and so on. So for that matter, we first introduce the notion of program points. So what is exactly a program point? A program point could be there in between two instructions or two IR operations, and so there could be a program point before each instruction, there could be a program point after each instruction, and we can see the effect of properties of execution of that instruction on what really happens from before to the after. So here are some program points which are shown for a simple CFG. What we have here is simple three basic blocks and some statements over here and some branching across and so on. So as you can see here, we have some kind of a branch here, conditional branch. This may be a fall through path, this may be a branch taken path and so on, and then again we have a fall through path here, and these dots show you different program points. So this is a IR operation which consists in the first basic block here, and then before and after this particular IR point or instruction point, we have two different program points. So there's a program point here at the beginning, then after this, after the second IR statement, after the if statement, and then you can see that we could have a program point right before execution of this particular instruction, which is a part of this basic block, and we could have another program point which could have been before this IR instruction right before its execution. Note that this program point, which is at the end of the B1, which is at the beginning of B2, and which is at the beginning of B3, they are all different program points because they signify different control flow orderings. This shows that before we resolve which way to go, this is a program point here, and then once we resolve, if we are going on a fall through path on the branch, this is a program point on the fall through path, the first program point on the fall through path, and here is a program point on the branch taken path, which is in this particular basic block, the first program point on the branch taken path. So you can see that they mean three different things and they should not be lumped together, and that relationship is cleanly captured by the concept of basic blocks, which really shows you where we are in terms of execution. Similarly, there is a program point now after this particular instruction, and so is after this particular execution, and so on. So you can see here that basic blocks could have multiple successors and predecessors, and those could all corresponding to different program points here. So as you can see, if you look at the execution of this simple program excerpt here, it starts over here and it kind of goes through each one of these different instructions step by step. And so there is a flow of information. something is going on before this instruction executes, something is going on after that particular execution, then something is going on after the second instruction, and so on. And finally, there is something going on at the end of this execution, and so on. Similarly, at each program point, you will have different kinds of things. If the branch is fall through, then something is going on right before we enter the execution on the fall through path. If we enter the execution on the taken side, we could enter it here, and so on. So first question is, in terms of what is going on in terms of program values, like this X and Y and Z and so on, what kind of information flow exists across these instructions? That's the first question that needs to be answered. And the second question is, how does the information flow between different basic blocks? Because obviously the information just crosses this particular IR operation, but at this particular point, which is connecting two different basic blocks, the information is flowing either this way and that way, and so on. So how does it flow between different basic blocks? That's the question to be answered next. So before we get into the details of the information flow and capturing that, which is called as the data flow relationship between different parts of these instructions, let's refresh our knowledge of intermediate code. So what we are going to ask you to do is, we have given you this simple program over here in terms of manipulating X and so on, and we want you to write the IR operations that are underlying this, which are generated by our IR code generator using that from the previous lessons. Try to analyze this while loop, this statement, and so on, and try to come up with, including the temporaries and so on, an IR that is generated over here. Please go ahead and write your generated IR as per the IR code generation algorithm in these boxes. Please go ahead and mark your answers now. So obviously the first statement is X is equal to 20. That is the IR code that is generated. The second one is, as you can see here, if the condition is false, we are going to branch out completely out of this particular loop, and that branch is shown to go to the last statement here by using this particular condition. We have flipped the condition here. If X, for example, is less than 10, then we continue execution inside the loop to show that we are branching out. However, we have taken a negation of this condition, which is X greater than or equal to 10. If that is the case, then we are branching out of this loop. Of course, if the condition is, this one is false, which means that we are going to continue execution inside the loop. Here it will be a fall through. And the first statement will be, of course, the first statement of the body of the loop, X is equal to X minus 1. Then the second statement is equal to X is equal to 10. And then let's take a look at the next statement here, X is equal to 4. Then we are going to execute certain statements. So we are going to take a flip of this statement again. If X is not equal to 4, then we are going to bypass these statements. Otherwise, we are going to get into the body of the if and execute that. And that's why we have a flip of this particular condition here, a negation of this condition, and a bypass, which bypasses the next statement, which is in the body of the if condition. And here is the IR code for the body of the if condition. We are going to, of course, come here if it's false. And at this particular point, you can see that the loop has ended. The if has ended and the loop has also ended. And we are going to branch back and start executing the next iteration. So we have to go and check again the if condition, which is controlling the execution of this while loop. That's why we have an unconditional branch here, which will branch back and start this execution again. And remember, this is what will be generated by our IR code generation. Again, in that particular lesson, take a look at the while loop, how it is being converted. There is a branch out, and then there is an unconditional branch which keeps executing the loop over and over. And that's the second one is over here. Of course, if the loop condition is terminated, or if the loop is terminated, then we are going to come here, and that's going to be the last statement, y is equal to x plus 5. And so this is how the IR code typically looks like over here. And please go ahead and check these answers as per the explanation which I gave. The other details that sometimes there is a temporary generated for x plus 5 into t, and then t is assigned to y. Those are a little bit simpler. We have tried to simplify this particular answer here by ignoring some temporaries and so on. But if somebody has come up with that answer, that x minus 1 first gets converted into a t, and then that t gets assigned to x, that is also an accurate answer. The important point here, of course, is to note that we have lots of control flow here. One is the jump out of this loop when the condition is false, otherwise fall through. And then we have similar bypass for if condition, and then a loop back for the while statement. And then finally we have a breakout out of this particular loop for statement 8 here, which says y is equal to x plus 5. So if the loop terminates, this is where we come and execute this after the loop is terminated. Now we'd like to reinforce the basic block concept. So we are going to take this IR and ask you to next divide this into the basic blocks and put the basic block numbers as we did for the previous lessons. So here is the IR that you just generated. Please mark these as B1, B2, B3 as per the basic block rules to find the leaders and so on. Please go ahead and mark your answers on the right hand side boxes now. So now let's take a look at the solutions to the quiz and let's see what your answers look like here. So the statement 1 belongs to basic block B1. And now the question is, what should we do with the statement 2? And we might somehow think that, okay, that should also be B1, but let's use the rules here. Is that a target of a branch? The answer to that is yes. This branch takes us here. So because of that, this will be a new leader. And so that's B2 here. Then the statement that follows, a conditional branch or return should be a new block. And so that B3, the statement number 3 should be in B3. Now, as far as the statement number 4 is concerned, it is neither a target of a branch nor it is following any conditional or unconditional branch. And so that should again be B3. So that's B3, statement number 4. If we go to the statement number 5, is the question that we ask ourselves, is it a target of a branch? The answer is no. So it continues to be B3. So as you can see, students, after the conditional branch over here, the statement which is following that should be a new basic block, a new leader, and therefore number 6 will be labeled as a new basic block. So in this case, we are going to give it B5 as the block number. Now, what about statement number 7? We might think that it is part of the same basic block which continues from here, but recall that we have a branch coming into number 7 from here, which will start a new basic block, and so therefore it is not a part of this current basic block. It's a new leader because it's a target of a branch, starts a new basic block, and that's B6. And then finally we have a statement which is number 8 here, which is also a target of this particular branch coming from the top. So that will be yet another block, and that will be B4. So you can see that we have applied these rules in different ways here. Each target of a branch starts a new leader. That's how we identify the starting points, and then we continue including everything until the new leader. Anything that is following a branch statement or return statement is a new leader, and that's how we started using number 6 also as a new leader. By applying these rules, we found out which are the leaders, and then we continued from a leader until we hit the next and included that in the basic blocks. So these are the basic blocks that you should get over here as shown. And then finally, here is the visual for the basic blocks, the way they look. And we start with B1 here, we fall through here to B2. There's a conditional branch there. This is the fall through side of the branch, which goes to B3. It executes these 3 statements. And again, at this particular point, at statement number 5, we have a conditional branch. Again, its fall through is here. Branch is taken, then it goes here. And again, from number 6, we have a fall through to go to 7 because it's not an unconditional branch statement, and there is a fall through condition between the two. So using the rule B that was given in the lesson on the CFGs, we are able to put this edge here. And then again, using the rule which is connecting, rule A, which is connecting the particular block to the target of the corresponding branch which ends it, we are able to put an edge here, directed edge this way. And again, following this path over here, we have the branch taken path here, or the target of the branch, we have put an edge here. Then finally, this is where the program ends, so we have an exit edge here. So please verify your solution. The labeling might be different. You might have flipped the labels as B4 over here and B5 there and so on, and call this as B5 something else. But exactly the structure should look exactly this way. The labels could be different based on how you gave them, but the structure of the control flow graph should exactly look like this in terms of the basic blocks and edges that are detected. So please check it. So students, having seen the CFG for this IR code, now we are going to continue and ask you some questions in terms of analyzing the control flow graph. And here are these questions. So for this particular IR, please name which blocks has more than one successor. The second question is which block leads to the exit for the program. And then the third question is which block has more than one predecessor. So what we want you to do is take this IR, detect basic blocks that you have in past from the previous quiz, then put it in terms of the control flow graph using the control flow graph algorithm, which puts the edges between the blocks and so on, form the CFG, and then using that CFG answer these questions. Please go ahead and write your answers now. So let us look at the first question. Which blocks have more than one successor? Well, let's take a look at the CFG for this, the control flow graph, and hope that this is the CFG that you got. And if you look at the CFG, you can see that we are interested in finding out those blocks which have more than one successors. So those blocks which have more than one outbound edges are the ones which we are interested in. And if you apply this particular logic, then it picks up two blocks which are highlighted here. B2 has two successors and B3 also has two successors. But if you really look at the other blocks, they all have just one successor, and therefore the answer to this question is B2 and B3. These are the blocks which have more than one successor. Let's now go to the next question. Which block leads to the exit for the program? So again, if you take a look at the CFG that you have gotten, and if you find out the edge which is to the exit node, the last block is B4, which goes to the exit, and so the answer here is B4. Let's look at the question which has the last one. Which block has more than one predecessor? So again, if we take a look at the CFG, and now we are interested in marking those blocks which have two or more incoming edges. If we do this exercise, then we can see B2 is one of those blocks, and the second block which has more than one incoming edges happens to be B6. Each one of them have two incoming edges. All the other blocks have just one incoming edge, and so they don't qualify, and therefore the answer to this question is B2 and B6. And so that completes the quiz. Please check your answers. Again, make sure the control flow graph that you have gotten happens to match the one which we have there. So having defined the concept of program points, students, and having reviewed the CFGs and the control flow graphs that are there for IRs and so on, let's now introduce the central concept which is very, very important for register allocation, which is called as the live variable analysis. So what is exactly a live variable at a given program point? Those variables which contains values computed earlier and needed later up further than that particular program point are supposed to be the live variables at that particular program point. So imagine certain variables which are defined, which contain certain values and which are flowing through that particular program point down, and they are being used further down somewhere in some expressions, in some conditionals, whatever, and their values are needed down from in the execution from that control flow point. If that is the case, then the variable is defined to be live at that particular program point. So what we are going to do is we are going to find out for each instruction a set of variables which are live at a program point right before I, which we call as in set of I. Then we are going to find out the set of variables which are live right after I, which we call as live variables at the program point right after I. And we are going to do something similar for a given basic block. We are going to define all the variables which are live at the beginning of the basic block B, called as in set of the basic block B. And then finally we are going to define all the variables which are live at the end of B, and we are going to collect these sets of variables and solve these solutions which relate these sets to each other and find out which variables are live where. Remember, here is something simple which we can easily deduce from these definitions which we introduced earlier. Consider a basic block and a first instruction I in that particular basic block. The inset of B is same as the inset of I being the first instruction in B, and the outset of I, which is the last instruction of B, is same as the outset of B. So if we find in and outsets for B, we can easily find the in and outsets for at least the first and the last instructions in the basic block. For other instructions, we'll have some similar rules to find their in and out sets which are sitting inside the basic block. So our goal in doing this solution is to find the inset of B, outset of B, solve all these equations which we are going to look at very soon, find the sets of live variables at the entry and exit of each of the basic blocks, and then from there determine where live variable set of each program point inside the basic block. So now, having seen the definition of liveness, what is it again? A variable is live at a given program point if it has certain assumed value before the particular program point, and that value in that variable is being used after the program point, then the variable is defined as live at that program point. So using this definition, let us apply this knowledge to the simple code excerpt here, and we would like you to identify the lines where B is live. In other words, B should have some value assigned to it before that, which is being used after that particular program point. If these conditions hold, then B is live. So with this simple control flow graph that is shown, which is modifying B by generating new values in B and using those values and so on, please mark those program points where B is live as per this particular definition. Please go ahead and mark your answers in these check boxes now. Now let's come to the solution of this quiz and find out if B is live or not. At the program point 1 here, let's ask ourselves a question, that is B carrying any particular value before this, and there is a use of this value after this particular point? The answer to that is no. B may have some garbage value sitting in it here, but nobody is using that value. If you see carefully from here, when we come down from here, nobody has used that value of B because B is not appearing on the right hand side here, and so therefore B is not live at this particular point, which is equal to 1. Now at that particular point, let's go to the next point. At that particular point, if a value of B is being given and which is being used after that particular point, then that point would be as live. So let's check that for number 2 now. And the answer is yes, because now we have a value which is assigned to B, and after this particular program point, somebody is going to need that value or use that value which is in B, which is defined here. How do we know that? Let's go down from here and see somebody is using this B, which means this B which is generated over here, which is A plus 1, is being used here. Similarly, that same B is being used here, and so on. So the answer to the fact that the value which is generated here is being used after this point somewhere down, the answer to that question is yes, and therefore B is live here. Similarly, applying the same logic, is somebody using this value B after this particular program point? The answer to that is also yes at 3, because B is being used here. And similarly, the answer to B being used here at this particular point at 4 is also true, because B is being used here. However, if we go to the next line here, you can see that at that point or further down from that point, nobody is using this B, and therefore the answer to that value, that question, whether B is being used, is false here, and therefore B is not being used. How do we know that? Because if you go further from this point, you can go on 2 different paths. One is this way, nobody is using B this way, and the second path is this way. Nobody is using B that way either, because there is nobody who has B on the right hand side here, and therefore the answer to that question is false. So what is the liveness here means, whether B is being used at that point or further down from that point, and both the answers are false here. However, these answers are true because somebody is using the value down from this point, somebody is using the value down from this point and including at that particular point, but nobody is using the value at that point or down from that point, and so therefore B is not live here, and similarly B is not live here. B is certainly also not live here because again the answer to that question is anybody using B from at that point or down from that point in the direction of control flow. The answer to that is no, and therefore B is not live here. So students, having seen the relationships between the instructions, the basic block and so on, the two basic questions we need to answer in terms of determining liveness is how does the information flow across instructions in terms of liveness information, and the answer to that is for each instruction I, what is the relationship between in of I and out of I. In of I determines the sets of variables which are live before the instruction executes, and out of I determines the sets of variables which are live after the instruction executes. So if we find these sets and a relationship between these sets, we'll be able to answer the question of finding out what is live before this instruction and what is live after this instruction. So here are those two sets that we are showing. We'll be able to find the set of variables that are live after this instruction, and then we'll be able to find the set of variables that are live before this instruction. The question 2 that remains to be answered is how does the information flow between the predecessors and successor blocks when it comes to control flow? And the answer to that is for each basic block B with successors B1 through Bn, what is the relationship between the out of B and in of B1 through Bn? So how do we establish this particular relationship with regard to the property of liveness is how it will determine the algorithm that will generate for finding the liveness. So again, here is the pictorial representation. Here is the out of B, the set of variables that are live at the end of basic block B. And here are the variables which are live at the entry of B1 and so on. And here are the variables which are live at the entry of Bn. How are these two related? That's what we need to find out. And using that relationship, we'll develop an algorithm to compute one set from the other. So to answer these questions, we are going to work through some simple examples and find the relationships first for instructions and then for basic blocks, and develop the necessary equations and then develop the algorithm. So what we are interested in finding out is how does the property of liveness of variables vary across the instruction. Here is a simple example, and here is the instruction x is equal to y plus z. Now you can see that the variables which are live at the beginning of this particular instruction here are the ones which have a use following that program point. So let us say we were at this particular program point and we are interested in finding out the live variables here. The question that we are going to ask ourselves is, tell me which variables are there which have uses after this particular point, whose values are getting used after this particular program point. And if we go and see this, we can immediately notice that y is being used here. What is the use of a variable? It is being used in terms of computing values from it, such as in the right hand side of this sub-expression. So y is being used, z is being used, and x is being defined. So if you answer the question in terms of which are the values which are being used after this particular program point, the answer is y and z, and therefore y and z are live at this particular program point. Similarly, if we go here and find out and analyze what may happen further from this particular program point, it may be that x is used somewhere down here and maybe z is used somewhere down here, so x and z might be live over here. Now, one other way to look at it is this, that as far as x is concerned, it is not live here. Even though the x might be used down from this particular program point, the answer to the question whether x is being used, current value of x that is in our hand is being used from this point onwards, the answer to that question is no, because there is nobody who is using x. In fact, a new value is being generated in x, so there is no use of the current value from here to here, and therefore x is not live here. So what you can see here is this, that certain values which may be live over here are not live anymore because of the redefinition. And what it means is a new value is being generated, so the current value has no use between this point and the generation of this new value. So something which is live here ceases to be live above the definition point of x, and that's why x is not live here. However, something which was live here might continue to be live up there, and in addition, something which was not live here, such as y, could become live here because there is a use of y now, and so there was no use of y down from here. But if you go here, you can see that there is a use of y down from here, and therefore y does become live here. So y was not live, y became live because from here to here we were passing a use point, and there was a use of a value of y down from that particular point. So y and z are live. X is not live because the current value of x, if you look at it from this particular program point, which is just above the instruction as the inset, there is no use of the current x here, and therefore x is not live. Let's continue this example further here. Again, there could be a use of this x down here, and there could be a use of some t down here, some temporary t. And now let's see what's going to happen as far as the live variables are concerned at the top. So there is a use of x from this point, but guess what has happened? If we just go rise above this particular definition point of x, the current x, which is the old value of x, is no longer being used at all between that point versus the point of generation of new value. And so x does not remain live at this particular point. Secondly, t remains live because t was being used somewhere down from here, and the answer to whether t is being used down from here remains yes, and so t remains live. And in addition, y and z are being used from this particular point down, and so they become live and are added to the live set here, even though they may not be live over here. So in short, what is going on is something which was live continues to be live provided it is not getting redefined, such as t. Something which was not live becomes live provided there is a use point in that particular instruction, such as y and z. And something which was live ceases to be live provided there is a redefinition of it, such as x, so it doesn't remain live at the top point. In other words, this clearly shows that we can compute the inset. So what is the general rule that we have learned from these examples? Knowing the variables live after a particular instruction I, can we compute the variables which are live before I? This is really important. We have to know the variables which are live after I, and then we can remove those which are redefined. They do not remain live here. The others do remain live here, and then we add the ones which are generated by this instruction as live variables which are used in that instruction, and that's how we get the live set here as in. So remember, the live set in of I has been computed using out of I. What did we do? We took the out of I, removed x from there, let t be there because there is no redefinition of t here, and then we added y and z which are a part of this instruction, and that's how we computed the live set at the beginning of the instruction. So let's see how we generalize this particular computation that we just looked at in terms of computing liveness across instructions. First, we compute what is called as the use set of I. All the variables that are used in the instruction I are live before I, because the answer to the question, is there a use of this variable down from here, becomes yes because of the uses in I. Definitions of I. All the variables that are live after I are also live before I unless I writes to them. So if there is a redefinition of a particular variable in I, that particular variable does not remain live before. And so here are the examples which are corresponding to this. A variable b, which the instruction uses, becomes live here. However, variable x, which was live here, which is redefined, does not remain live here as per the second rule. And then whatever was live after this particular instruction, which is not defined in this particular instruction, remains live here, and the examples are y and z, again the use of second rule here. So mathematically, the equation here is inset of I, which is the set of variables which are live before I, is equal to outset of I, the variables which are live after this instruction I, minus def of I, the ones which are defined in I, those are removed, like such as x in the previous examples, and union use of I, the ones which are used in instruction I, get added as the live variable here. So that's the equation. In of I is equal to out of I minus def of I. So we are taking out the ones which are defined in the instruction, which have L value in that instruction. We take those out, they no longer remain live. And the ones which are used in that instruction on the right hand side, or R values, are added through the use of I, and those are the ones which are live at the beginning of the instruction. So let's take a look at this simple code excerpt and see what all is live when, and we'll use these relationships between instructions to come up with the set of live variables here. So for that particular purpose, we are breaking them down into different instructions, and we are going to write the relationships between these instructions. So live 1 is the set of variables which is live here at this particular program point. Live 2 is the set of variables which is live here at this program point. Live 3 is live at this third program point, and finally live 4 is the one which is live at this particular program point. And what is a live variable means? If we look down from that particular program point in the direction of the control flow, there has to be some use of that particular variable along at least one of the control paths. And if that is the case, the variable is live there. So you can easily see here that first the equations are as follows. These are the instructions I1, I2, and I3. The set of variables which are live here is live 4 is same as out of I3, outset of instruction 3. Live 3 is same as out of I2. This is the second instruction. So this is outset of second instruction is same as live 3, and is also same as inset of instruction 3 here. If you continue this, live 2 is equal to the outset of instruction 1, out of I1, which is also same as in of I2, the inset of instruction 2, and then similarly live 1 is equal to the set of in of I1, which is the inset of instruction 1. So those are the sets which are mapped on to these in-out sets, and now we'll connect these in-out sets as per our definitions or the equation that we have seen. So now we look at the relationship between the live sets. So what is it? If you can clearly see here, the live 1, which is the set of live variables here, is given by live 2, which is the set of live variables here, minus x, because x has been redefined, and union use of I1, the variable which has been used in I1 is y, and so union y. So this is the equation that we get here. Similarly, live 2, which is the set of variables which are live at the entry of instruction 2, is equal to live 3, that means variables which are live after instruction 3, minus y, because that has been redefined, so it will no longer be live at the entry here, and union z, the use set of instruction 2, and that's why we have z here. So that's another equation. And then live 3 is the set of variables which are live here, is given by live 4, whatever is live here, minus whatever has been defined in terms of L value here, and that set happens to be null. There is no definition here in the if statement. There's only a use, which is d. So everything that is live here remains live. Nothing is removed because of redefinition. And in addition, there is a use of d here. So that gets added here through the use of that particular I is getting added here, which happens to be d here. And that's why this particular equation. So I hope the concept of liveness is very clear here. What it means is we are trying to determine the answer to a question. Is somebody using this value down from this particular point, at least along one of the control paths? And if the answer happens to be yes, then the variable is live. If the answer happens to be no, the variable is not live. Now, how do we cast this relationship? The relationship is very clearly expressed by this simple equation, which tells us that whatever variables which are live after a particular instruction, they remain live provided they are not redefined in that instruction, because the answer to that question remains the same if there is no redefinition. But in addition, if something else was not live after this instruction, all those variables which have uses in that instruction will get added to the live set, and so we add those, and that gives us the set of all variables which are live at the entry of this instruction. So this is a very important equation to be noted. In is equal to out minus def union use. Now let us apply our knowledge of what is defined and what is used in these instructions. Let's find that out first using this simple quiz. Again, what is a definition? A definition is an L value. If some value is being defined as an L value, there is a store into that particular value that's called as the definition. If somebody is using that value in a particular IR statement on the right hand side or as an R value, then that's a use. So what we are going to ask you to do as a first step in determination of liveness is take this simple code excerpt over here, and for each of the statements tell us what is the definition set of this statement and what is the use set of this particular statement. So the variables which are being defined in this statement you are supposed to write here as def. The variables that are being used by this statement you are supposed to write here in terms of this use. So go ahead and take a look at each one of these statements, come up with these lists, and please go ahead and write your answers in these boxes. Go ahead and write your answers now. So if we start analyzing each statement by statement, let's go to the first statement. There is a variable a which is being written into by this particular statement, or it's being defined. So that's a def set. It's an L value. There is no use set here. There is no variable which is being used on the right hand side of this expression because it's used as a constant. So that set is null here. Let's go to the statement 2. The variable which is being defined here or being written into is b. The one which is being used to compute other values in an expression on the right hand side as a R value is a. Similarly over here, the definition set here is c, which is being written into, and the use set in this particular case in fact consists of two variables, b and c, because there are two variables which are participating in this sub-expression. Again, applying this logic, a is being written here and b is being used, so that's what is going on. And again, for this particular statement number 5, there's nobody who is writing into any location, so only use is there and a is the use set of this. And finally, if you continue to 6, only c is being used as the return value. There's nobody who is writing or modifying anything here, and so the def set is null here. So these are the answers to the def and use sets for each of the variables. Please check those. So again, recall that we had this nice equation which told us how do we determine the set of variables which are live before an instruction using the same set after the instruction, and by subtracting from that set the ones which are defined in that instruction and adding to that set ones which are being used in that instruction. So keep this equation again in mind, and let's now see how to proceed further from here. Remember, this flow of information is backwards. In other words, there is a direction in which control flow proceeds in the program from one block to the other in the direction of arrows and so on. But this information is computed in the backward sense. So we need to find out outsets before we can compute the corresponding insets for each of the variables. And so that is why this is a backward data flow problem. The reason is the propagation of information is in a direction opposite to that of control flow, in a backward direction, and that's why it is called as backward data flow problem. As you can see here, by computing liveness at 4, we are able to find one which is at 3. By subtracting any definitions and adding any uses, we compute this by using that. We compute live 2 by using live 3 in a similar way. We compute live 1 by using live 2 again in a similar way. And so we are going from this direction to that direction. By knowing live 4, we are computing live 3, then live 2, and then live 1. So the direction of computation is opposite to that of the flow. The control flow is this way, the direction is opposite. And that's why this is called as a backward data flow problem. Unlike this particular problem, many other optimization problems are forward, such as constant propagation and common sub-expression elimination, available expressions, and so on. Those are forward problems where outset is computed from inset, whereas in our liveness problem, inset is computed from the outset, and that's why it is backward. Let's now analyze the implications of control flow on this liveness analysis. So far we had looked to what happens across the different instructions which are in a given basic block. But now we must extend the technique to what happens across the basic blocks. So what is the relationship between a particular basic block and its successors in terms of liveness computation? So here are some other examples, and they should help us to really formalize this particular relationship. So the relation is again backwards. by knowing the liveness here and here, we are able to compute the liveness here. For example, if a value is live here, such as x, it will be remaining live here. If some another value is live here, such as y, it will remain live here, and such as z, it will remain live here. So in other words, as long as the value is live in either in of b1 and in of b2, it will remain here. If it's not in either one of them, such as q for example in this example, is absent from b1 and live sets, so it will not appear as live here. However, if x is live here, x is live here, it will definitely appear there. Y is live here, y is not live here, still it appears as live here. And z is reverse, it is live here, it's not live there, it still appears. So in other words, a variable appears here as long as it's live in one of these insets here. Similar observation can be used here. If a variable is live in b1 or in bn or in b2 and so on, it will remain live at the exit of the predecessor basic block. That's because the answer to the question, is something live from this point onward, it's automatically yes. If it's live here, then obviously the answer that this variable is live is already yes, and that tells us that the variable continues to remain live over here. So here is the big rule that we saw that is embedded in those illustrations in the backward slide. A variable is live at the end of a basic block B if it is live at the beginning of any of the successors of B. So mathematically speaking, out of B is equal to union of B dash, where B dash is successor of B, in of B dash. So all the insets of the successor, if we take their union, we get the outset of the predecessor. So again a backward relation here, because whatever is live in one of them automatically remains live in the predecessor's output cell. Again, this is a backward relationship, and again, as you can see here, as long as the variable is live along one path, it remains live in the exit of block B. So now what we are going to extend you, having understood the relationship between out and insets across basic block and out and insets across the instructions I, we are going to ask you to apply this to this simple example which is shown here, and you already computed def and use sets. From there, and using this example, we want you to compute out and in sets, which are the sets of variables which are live at the output of each one of these basic blocks, and which are live at the entry of each one of these basic blocks, which are marked from 1 to 6. So go ahead, use the definition and use sets, use the formulation of what is exactly a live variable, come up with those sets which are live at the exit, use again the rules 1 and 2, and write all the sets that are live at the beginning. So please go ahead and write your answers now. So let's now take a look at the answers. So let's start with the last statement here, because as we know, the liveness analysis is a backward analysis. So it will be easier to follow the answer starting with the last statement of the program and working our way back to the first statement of the program. So the last statement is returning C. This statement is not really returning anything. So the outset of this particular statement is null, and the inset, which is the live set, is C. Why is that? Because nothing is defined by the statement, but what is going on in the statement is we are using a value of C on the right hand side. So this is a R value which is being used here. We are returning the value of C here. We are not putting any new value into C's location, but we are reading a value out of C and returning it back as part of the return statement. So this is the use point of C. And so because of this, the value becomes live at the beginning, although it was not live after this point. And of course, there is no definition which is being done by this particular statement. Next, we are going to go to statement number 5. Again, statement number 5 is just using a variable here, which is A. And so the use part of this particular statement is only A. Nothing else is being defined here. So the defined part of this statement is null. And as you can see, because this particular C was live here, and if you trace back here, what is going on here, A has been used after this particular point. So the live outset here is A and C out of 5, and there is nothing being defined here. No other thing is being used, and so because of which the live in set is also A and C. Why was the live out set A and C again? Because C is being used this way, A is being used this way. So the union of the two live in sets here, which form the live out sets here, included both C and A. So this is the answer here, why that is live out is equal to AC and nothing being redefined, so live in is also AC. Now continue this further down in a backward manner. Remember, we are going backward because liveness is a backward analysis, so we are following the direction which is reverse to that of the control flow. And so the live out here is equal to the live in here, and so that is why we have live out of 4 is same as live in of 5, which is AC. But now let us see what is going on in this particular statement. A is being redefined and B is being used. So out of AC, we are going to remove this A because of its redefinition. We are going past the definition point now in the backward direction. So at this particular point, the current value of A is no longer live because there is no use of that value before a new value is being defined. So we took out the def from the outset. The def set contains small a, we took it out, and that's why we are left with only C here. But the use set, as you can see, what is being used in this statement includes B. So B is getting added here. So the outset is AC, which is same as the inset here at the entrance of 5. But then what we did from that AC, we took out A because A is being defined. So it's no longer live here. And then we added to that, only C was remaining there. We added to that B because B is being used, and now so things which are live at the entry of 4 include B and C. Keep continuing further here. The live out of 3 is same as live in of 4. So out is same as the in. So that's why BC is the set of variables which are live here. And as you can see here, although C is being defined, it's not the upward exposed use. So C is, there is another C which is being used on the right hand side, and so as far as C is concerned, it could get removed, but it gets also added because of the use point here. So what is the definition point? C. So the C which was live here has been removed because of the definition, but was added again because of the use here through this particular statement, and that's why live in of this particular block also remained as BC. The other variable which in fact remained the way it was B, because this was live out here, and in addition there is a use here. Even if there was no such use here, B will remain live because there was no definition point of A inside this 3, so B will remain live. So in this particular case, we have B and C which are live at both entry and exit of this number 3. And then if we continue backwards, live out of 2 is same as live in of 3. That's why we have this BC here. Now out of this BC, you can see that we have a definition point of B here. And so we go past that. This B was live down from here point. But when we go up in terms of a definition point, if something was live down, it is taken away because of the definition point. And that's why from the output. So having seen the liveness and found the equations which relate the sets in and out across the instructions and in and out across the basic block. Now let's define it formally and come up with an algorithm and a detailed example in terms of how to compute the live sets. Again, they are backward, computed in a backward manner. And here are the equations. The set of live variables at the exit of a basic block is the union of all the variables which are live at the beginning of the successors of that block. Similarly, a variable which is live at the beginning of an instruction can be found by using those which are live at the end of the instruction, subtracting from those which are defined in that instruction, and taking a union with regard to what is being used in that instruction. So this system is often called as a system of data flow equations and is the one which is solved across basic blocks, and that gives us the set of variables which are live at different program points. The way we will solve this particular system is that we'll try to find out first the use sets of each of the instructions, and we'll try to find out the use sets within a basic block, set of definitions within a basic block, and then we'll propagate these live sets across basic blocks, and we'll iterate till convergence, till the sets don't change. As far as the loops are concerned, these circular sets of dependencies are solved through iterating upon them. When the sets don't change, we are going to stop propagating the sets. because they would have converged by then. Again, as I mentioned, it's going to be an iterative solution for computing these sets locally, then propagating them, and then each basic block will start with an empty set of live variables, iteratively apply the constraints for finding things from them, and then when none of the sets change, we have reached a fixed point, we are converged, the sets don't change anymore, and we'll stop. And that the contents of those sets gives us the set of live variables at each of the points. So here is what we do as an algorithm. For all the instructions, we define their in and out sets phi, empty. Then for each instruction I, we are going to find out its set of in set by using the current out set, subtracting the things which are defined in the instructions, and then adding the use set to it. So as you can see here, because this set is phi, initially all the in sets for each instruction will consist of its use set. We'll use this initialization of each of the in sets for the instructions, and then we'll go across the basic blocks by computing the outset of a given basic block using the inset of the successors. And then in turn we'll bring this outset into the current basic block over here, and then compute in a backward way the respective insets for each of the instructions and the inset of the basic block, and then we'll substitute that again to compute the outset of the predecessor of the block, and we'll repeat this particular process. And when the sets don't change, when all the values are propagated, we will stop. And that's an iterative algorithm for finding the live sets. Remember that the convergence is guaranteed here because these sets are only growing monotonically, and at certain point, if all the values happen to be live everywhere, then the sets stopped growing, and therefore the termination of the algorithm is guaranteed because there will be no change in any of the sets. So how are we going to do this particular problem? Here are again the steps. Set up live sets for each of the program point. Initiate those equations for each of the instructions. Solve the equations by propagating them from the insets of the successors to the outset of the predecessor, and continue this propagation through the basic block to its own inset. And when all these propagations stop in terms of growing the sets, when the sets don't change, for example, when all the insets are stable for all the basic blocks, none of them change, and when all the outsets are stable, when none of them change, even after propagation, that basically means that we have converged, all the values of live variables have been propagated through the control flow graph, and so it doesn't grow anymore, and that's the termination. The sets which are computed at that particular point give us the sets of live variables at the entry and exit of each of the basic blocks, and in fact, same is the case for these sets across instructions. Here is a simple example which we are going to use to compute these sets. It's a CFG. You can see that certain values are being used here, certain are being defined, and so on. So there is a def set here. For example, here is a def set consists of X. Use sets consists of Y and Z, and we'll use this to compute the live and in and out sets using the relations which we saw earlier. So here are different program points that we defined first, L1 through L12. These are again before and after instructions, and some of them coincide with the inset of a basic block, and some of them coincide with the outset of a basic block, such as L6 coincides with the outset, L3 coincides with the inset. And what we are going to do is form these relationships for each of these instructions using the set relationships we saw earlier, and then propagate them across, and then when they stop propagating, when they stop changing for all sets, if that happens for all basic blocks, then we terminate. So let us start by first listing the def and use sets for each of the instructions. So for each instruction, let's such as statement 1, what are the definitions? There are none. What are the uses? C is the one. Similarly, if you go to 2 onwards, for 2 it is X is defined, Y is being used. For 3, Y is being defined, Z is being used. For 4, nothing is being defined because there is no L value here for this if statement. The value which is being used, however, happens to be D. Similarly, if you go to statement 5, x is being defined and y and z is being used. For 6, z is being defined and nothing is being used. For 7, z is being defined and x is being used, and so on. So for each statement, we have defined what are the values that are being defined and what are the uses that are being generated. And then using these equations and the algorithm that we mentioned, we are going to first come up with the values which become live locally for each one of these in and out sets, and then we are going to propagate those globally using the second equation. For example, whatever is the value which is live here and whatever is the value which is live here, we are going to compute that to be a set of values which are live at the exit of B1. Because out of B1 is equal to in of 2 and in of 7. So we are going to use such relations to compute these, and then we'll propagate them across the basic block using first equation, and then propagate that further using in and out relationships using second equation, and we'll keep doing this till convergence, till none of these sets change. So if you do this exercise, we can easily see, and the easiest way here would be to start at the exit because this is a backward problem. Let us see what happens here. We'll try to work out through 1 or 2 and the rest you can verify if this is right. So the values which are live at the exit of 7 are null because there is no variable is being used after this particular point. So this live variable set here at the out of 7 is null. However, since there is a use of x here, in 7, if you look at the variables which are being used after the entry of 7, if you notice it, it will be just x, and so the live variable set for the entry of 7 is equal to x. Next, let's go to the live variable set which is the out of 1. So live out of 1, you can see that the x remains live here, and if you look at the live variable set from this side, it will be this y, z, d will be another one, and further down it will be c because c is being used here, c will get used here, and c is being live here. So c is being used here. You can see c, whether it is being used downhill from this point, the answer is yes, 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 and then finally c is remaining live here. So by doing this backward propagation of c, you will see that y, z, d, c, and then x coming from here all are live at the exit of 1. Now nothing has changed as far as 1 is concerned. There is only use, so none of this is killed because there is no redefinition, so all of these remain live, including c, which was already live. Similarly, if you keep applying this logic and propagating these sets from what is computed to be locally live for used within that instruction, take that particular part, propagate it to. So let's take a look at a little bit wider perspective of the data flow solutions here. Let us look at what did we see as a special way of doing this data flow analysis for liveness. A data flow offers a common framework for such analysis, computes the information at each program point, and it propagates it in a conservative manner, either in a forward or a backward direction. In this case, it was propagating it in a backward direction. That's why liveness is a backward data flow analysis. And this allows us to find out the live intervals in which a particular variable is live. So what is a live interval? A live interval is when the variable just becomes live. It was not live before, it just becomes live. And when is that the case? It is at the definition point is when the live interval starts. When does the live interval end? The live interval ends when the variable just becomes dead. It is no longer live. So which is the last use point. So variable was live before this particular point but is not live after that point. That is the last point in the live interval, and the set of program points in between is included as the range in which the variable is live and should be given a register. So that is the use of this particular information in terms of deciding what are the sharpest points where the first time the register should be given and what is the last point from which the register should be taken away. And this interval is between the starting of the liveness and the ending of the liveness is what defines these two endpoints, and that is called as a live interval.